Hello, this is Tuesday's lecture for week 13. We're finishing up lab 10. So last week we did parts 1 and 2 for lab 10. We made the, what did we do? The decoder. We added these 5 opcodes, the jump opcodes. And we also made a control unit, which incorporated the decoder, and also was the way we were able to institute this 4-step instruction fetch cycle. So the first one to get the opcode, the second one to get the high order address bit, the third one for the low order address byte, and the fourth one to execute the instruction. So now we just need to finish this up. We have a couple more, one more circuit to make a program sub-circuit, and then we get to modify the ALU a little bit and put it all together with this beast. So one thing I did without you last time, the way we left it was this was a little more scrunched together. So I just moved these, they were over here someplace like this. So I just moved this over to the right because I know that just looking forward to the end of lab 10, we're going to need a little bit more room to put in this control unit, and so I just moved things to the right and I put the instruction decoder flat like that, but otherwise no changes. So if you haven't yet made the control unit or done added these opcodes to the decoder, please look at last week's lecture to do that. Okay, so the first thing we need to look at is step 3. So we're going to make some modifications to the program counter. Right now we're just using this program counter. We're just using it as a dumb ring counter. And do you remember from your last lab, let me see if I have that here, the ring counter lab, so sorry, 2 labs ago, we didn't have this. This was, our ring counter just worked like this. You'd just make the clock go and it would count. Oops. What's going on? I took out some stuff. I forgot my feedback loop here. It just made the counter increment from 0 to 3, or whatever level we originally had these set at. But if each of these latches has some extra capability that we weren't using. One of them is, remember, each of our D-type flip-flops had a preset and a clear input. And with preset, we could set this to any, let's say we wanted to start at 2. First, let me clear this. If we want to start at 2 instead of at 0, I could just set it to 2. And then I start my clock. Now it's going to 3. Remember, this is the least significant bit, 4, and then so on. So this is the capability we're going to use, and we're going to need this for the jump command because we want to be able to set any address into the ring counter, just to go to any of the 65,000 plus addresses in memory. Okay, so to add some of this functionality to our program counter, we're going to take this out of our main circuit, and we're going to make a new circuit called program counter. And I just hit Control V to paste that back in there. It's still a 16-bit counter, good. And to have all the functionality we had before, we're going to need a clock input. And we're going to need a reset. I don't know why it keeps doing that. Oh, and we need an address out. So remember, the circle is the out, and it's a 16-bit address. So 16 is right there. But, yeah, 3-state, no, good. Okay, I'm going to give that a name. All right, well, let's see what this looks like. Let's put these down here. What is this anyway? That's my reset, and that's my clock. And that's my output. Alright, good enough. Let's put that in our main circuit now. everything hooked up? Yes. Okay, so now I should have the same functionality I had before. Let's maybe call this, come on. I'm trying to get fancy here with my escape codes and I used the wrong one. Wow. Anyway, okay, so yeah, so it finally worked. The backslash ends an escape character. Remember from early chapters in Petzold we talked about this. You've probably already seen this in your JavaScript class, but I wanted to make it 2 lines instead of 1. It doesn't look great yet, but we're going to replace this really soon. So let's just make sure we have the same functionality we did before. Yeah, it looks like it's still stepping through the program, and if I want to reset it, it still goes back to 0. Perfect. All right, next. Yeah, we did that. Okay, now we're going to add some more capability to the program counter using the set and reset options. And here I hope you will agree that I've outlined the reasons why we need to make this complicated looking circuit, but basically we just need to make this circuit. So I'm going to go ahead and do that off camera. I think that you're familiar enough now with Logisim that you know how to insert all of these things, including the multiplexer. So I'll go ahead and do that, and I'll see you in a minute. Okay, I'm back, and I've just copied basically the circuit from the lab into Logisim. See, the only sort of strange things to mention are that this register needs to trigger on the falling edge, and what else? That's it. Okay, so there's this part of the circuit here that I haven't filled in yet, which I'm asking you to do. But before I do that, I just want to walk through how this circuit is working. Because if you remember, on our 4-step instruction cycle, we have 3 steps where we're going to memory to get the opcode for the first step, to get 2 bytes for the high and low order bytes for the memory that we want to go to, that the instruction refers to. For example, if we want to store something, then the next 2 bytes are going to tell us where to store that. Or if we want to load something, the next 2 bytes will tell us where in memory to go to retrieve that information. So the 4th step in that instruction fetch cycle, we don't actually want to advance the clock, right? Because we only have 3 locations in memory that have been used, 1 for the opcode and 2 for the memory that opcode refers to. So on the last step, the execute instruction step, we don't actually want to advance the clock. So that's the purpose of this. On our execute instruction flag, if this is set, in other words, if the execute instruction flag is set, then this input to the AND will be low and the clock won't have any effect. That's what we want. There's one exception to that, and that's that if we jump, let's say I want to jump to this address, then I do want to update, I do want to set this clock, I do want the register here to update with this address. That's if I have a jump and I'm not in the execute instruction step. So let's make sure that happens. It does. So this has updated with the new address. Now, proceeding from there, remember the jump opcode is still going to be active for the next 3 instruction cycles. So when I cycle the clock, it's incrementing like it has before. So that seems to be working as intended. The part that we need to fill in is we also have, actually we have a total of 5 conditions, but we're just doing 3 for this lab. We have jump if not 0 and jump if not carry, because that's all we need to implement the code that Petzold has. When you're actually programming your machine later, as in for the final exam, we're going to have all 5 of the jump flags implemented. But for now, this will be good. So what I will do is I'll show you what we need to do for jump if not 0 and the 0 flag. so we've just demonstrated how you can load an address into the program counter with the jump command. Well, if another possibility is, let's say that the zero flag is set, and we'll talk about the zero flag in a second, but that's looking at the output. If the output is zero, then the zero flag is set. If the zero flag is not set, that means that the accumulator output is not zero. So that's the condition that we're jumping on. We have a jump if not zero, we have a jump if zero. This is the jump if not zero. So what we need is an AND. I need, I don't know, let's try this. So if jump something like this, something but not quite like this. So now if we have a jump if not zero command, this isn't lit. It's not lit yet because our zero flag is not set, right? If jump if not zero, we actually need to have the zero flag set, right? Jump if not zero. Hold on, let me think. Jump if not zero. So zero has to be not. Yeah. So that means this needs to be inverted. Okay. Now if the zero flag is not set and we have a jump if zero command, then jump to that address. And I just pulled this out to fix that double overlap. So if you wouldn't mind, think about what this situation needs to be. It's not going to be very different from this one, obviously. And go ahead and implement that in your program. And then we'll be ready to give it a shape. And I'm guided by the picture at the back of the lab. We're working on the program counter. So we want the program counter inputs to be like this, where our jump instructions are going to be across the top, our flag outputs on the left-hand side, clock, reset, and execute instruction at the bottom. So I think we went over this last time, so I'm not going to bore you with those details. But what I found to be a really useful trick is to use a tool like Snagit to just take a picture of this, so I know what I'm looking at when I go to this other screen. If I'm trying to drag these inputs here and I click that, it's tiny little, it's really hard to see. Like, can you figure that out? No, you can't, unless you're looking at this picture. So I'm going to do that off camera, and I'll be right back when that's done. Okay, I'm back, and I've just modified the shape so that these outputs match the picture here, where I've got all my jump commands on the top and my carry and zero flags on the left-hand side. Yep. And then the output is here in the middle, and the data in is in the upper right-hand corner. Great, so that finishes up number 3. Now we just have to modify the ALU a little bit. And if you did the last lab, your ALU will look like this. Is the ALU we had for the Harvard machine. And one of the things that I had to do was had to have these 2 8-bit registers, and part of the reason was because after an add operation, we would we used every cycle of the clock to do something, and if we weren't actually adding something, then that carry out would be lost. And now we don't need this anymore, right? Because one of the advantages of this system is that you'll notice on the last page of your lab, instead of the clock going to the program counter and the ALU and the control unit, the only thing that makes that advance, well, that's not true, sorry. I should say the ALU and the program counter. What makes it advance is the execute instruction. So the ALU clock now has been replaced with the execute instruction command. So we don't need this anymore. But we are going to, you know what, I'm going to leave that in there because we're going to use another register anyway. We're going to use it to hold the zero flag, except this is going to go away. So let's pull this out. Bring that down. And let's bring this out. Alright, so you'll notice in the lab that we're adding this comparator, and we are going to use the carry flag as one of our branching conditions, and the other thing that we're going to use is the 0 flag. So if, for example, if we subtract two numbers and we get 0 as a result, we can use that as a basis for making decisions. In fact, you'll see, it's surprising, but all of the if-then statements that we can create with a program like JavaScript can actually be implemented in machine language just with these flags, the carry flag and the 0 flag. And we'll get to test that out by doing some machine language programming ourselves here next week, provided that you have a working von Neumann machine. Okay, so comparator is in the arithmetic section on the left, and let's see. Let's put it here. And I want to look at the output, and I want to compare it to 0. So you can pull up the help if you want, but these outputs are self-explanatory. It'll be high if A is greater than B, and this is A, and that's B. So I want to compare it to 0. I want to see if it's the same as 0 or not the same as 0. So I'm going to be looking at this output. And to compare it to 0, I need to give it a 0. So let's go under wiring, constants. And these are 8-bit numbers that we're dealing with, right? So let's give it 0. And we see right now that the output is 0, and it's equal to 0, and so this lime green indicates that that value is high. So this is our 0 flag. Make this face out. Okay. Great. I think our ALU is done. That's the only change really to the ALU, right? Let me just make sure. Yes. Oh, set your latches to trigger on the falling edge. So let's make sure. That's rising edge right now, so that needs to be falling. And that needs to be falling. Okay, yep. Fantastic, we're done 4. Now, now we get to do 5. So we get to take all of our, how does this look anyway? Oh, no, we have a new output here. What is that? That's my 0 flag. And where do I want that? On the right. That's carry. 0 is right below it. And that's my output. Boom. Okay. Great. So, this is the output now. Our 0 flag is here. And we need our program counter. So it's too fat. Clock, what is that? Reset? No, execute instruction. So I need an execute instruction input, don't I? Oh, no. That's going to come from our instruction decoder. Oh, we're getting rid of a lot of stuff. In fact, this goes away now. Oh, so much of this goes away. This isn't the data RAM anymore, it's just the RAM, because there's only one. Remember, that's one of the two main characteristics of von Neumann. We just have one RAM for both code and data. Let's see, what else can we do? Well, let's put our control unit in. Control unit program counter ALU. Yeah, looks good. All right. So, gosh. All right. So that's our address out. This is the address that we're going to get from the control unit, and I forget where that output is. Let's see. That's the clock. I'm going to put a tunnel here. It's more of a label than anything at this point. Yeah, that's going to be the clock for our accumulator. And for our ALU, okay, it looks like we need to run the clock to memory and to our ALU. No, wait, no. To the control unit. Come back. Is it going anywhere else? Nope. Okay. And then I'm just going to wire the rest of these up. This is my address from instruction. That's the address from instruction, output, address. Okay, all my jump commands are here. So this should be jump, which is this one. Somewhere. Looks like maybe I got it in the wrong place. This one's jump if not 0. And this one is jump if not carry. These are our flags. Oh, we use tunnels. Using Control C and Control V, and then the right arrow to turn the thing around. And these are load, left arrow, store, using left arrow, Okay, I think this is kind of boring to watch, so I'm going to skip ahead until I've finished all these connections. I'm just making sure that these outputs match these inputs. Okay, I matched all the outputs of the control unit to the inputs of the ALU. Now I've got to give it an execute instruction right here. So I'm going to copy this tunnel. And looks like we are done. Woo! Okay, so let's try this out now. Let's see if we can actually program it to do something. The simplest thing I can think of to do is add two numbers together and store them at some other memory address. So now we're going to use the awesome power of the the von Neumann architecture. Oh, it looks like I left something out. Sorry. Okay. Store. Right. We're using this store functionality. This store if one stores an input to memory. So it's not enough that we have a store command to actually load something into memory. We have to have a store command, and we have to be on the execute instructions step. And so we just need to put an AND gate in there to make that happen. Execute instructions right here. Something like that. Okay. And it doesn't look like I left anything else out. But let's find out. Let's write a program. So load is 10, I think. So I'm just using the keyboard to type these in. And now we need to tell it where to load the data. And the nice thing about this is we can have our data in a completely different area, part of memory, than our program. And we don't even have to use consecutive memory locations to write all of our program. Let's just say right now I think I'm going to write a really short program, and so I'm only going to need the first 20 or so memory addresses. Actually, I won't even need that many. So I'm going to put my data starting at 0030, and I want to store a 22 there. So to tell it, my high order address byte, that's these two digits, is the higher order byte. The low order byte is these second two digits. So my high order byte is 00, and my low order byte is 30. So that's telling us load whatever's at 0030. And then I want to add I think is 20, whatever is at the next memory address, which is 0031. So there's the high order byte, 00, and 31 is the low order byte. Okay, now I want to store that result someplace, and store is 11. And the location I want to store it is, I don't know, let's go crazy. Let's put it down here at 0040. Oh, I didn't tell it what to add to. Okay, I loaded something at 30, and then I added it to something at 31. So 31 needs to be my second, what do you call that, add end? And then, yeah, so I want to store it at 0040. And then finally, we'll stop the program execution with FF. Okay, so I expect that to have a 55 here at 0040 if I wrote this program correctly. So when you're done writing your program, go File, Save. And you can also cycle through the memory on here. If you hit the Enter key, well, with the poke tool, if you hit the Enter key, it will go down one address line at a time. If you hit the backspace key, it'll go up. But anyway, I think it's much easier when we're writing these programs to use this. All right, let's give it a go. First reset to start at 0, and then let's start our clock. So it correctly read load, and it should have loaded a 10 into the. It should load a 10 into the accumulator. Oops, what am I saying? No, we're going to go to 0030, and whatever's at 0030 is going to get loaded into the accumulator. So second fetch cycle, fetch the high order byte. Third is fetch the low order byte, and now let's Hopefully it zooms down there to memory. It did. Now it's at 0030, and it just loaded 22 into the accumulator. That's execute instruction. Okay, now notice that we're back to 3, right? Once the jump command was no longer lit, it goes back to its normal programming, which is just incrementing the counter. And the next address is 003, right? This is 0002, this is 0003. And that's giving us an add operation. Let's see if it finds that. Yep, so that lime green indicates that the add, it might be convenient to put labels here. So add is lit, and now it's going to go to 0031 to get the data to add. Yeah, so it zoomed down here to 31, picked up 33. And we should store the result, which should be 55. I'm a little distressed that I don't see this in the accumulator yet. Add 0040. Okay. Oh, I see. I made a mistake. Here, this is my. I was outsmarted myself actually. This is my data out, and this is my data in too. And I did that because I thought it would be easier to route things. So I've got to switch these lines around. So that's my output. And that's what I want. Okay, so it looks like the mistake I made was I forgot to set my accumulator to falling edge. So make sure you make that change, because with Harvard Machine we're using rising edge for almost everything. So now the accumulator has to be set to falling edge, and I think we're in business. Let's just do one more walkthrough on this program. So load whatever's at 0030. So it's loading a 22. That looks good. Next is add whatever's at 0031. So it should go to 0031. It does. And it outputs 55. And then it stores at 0040. So yeah, perfect. And then we hit the Alt and no further. I'm not going to make any more progress with the program counter. Alright, well that wraps up Lab 10. I think we'll be ready to write some machine language programs next week.